Last time we started our chapter on error detection and correction, and we saw how what is the overall scheme for detecting any error. We saw that the sender adds some redundant information which is generated through software component that is called generator and added with the message. We use proper word that is appended. Appended means added at the end. And you saw in our headers that the last field in our frames on Ethernet as well as on our wireless network, the last field is the extra or the redundant information that is used for error detection. This message is sent on this whole process on the sender side, it is called encoding, and the component software component that does this whole work is called encoder. On the receiver side, receiver, there is a component that is checker. The checker receives the message as well as the redundant information. From the message that it receives, it also generates once again the redundant information or the extra information for error checking, and then compares the information generated by the receiver as well as the extra or the redundant information that is sent by the sender. If both of these redundant information match, it says that it considers that the message is intact, there is no error, and it accepts the message and discards the extra or the redundant information. Otherwise, it says there is an error. Okay, how we can add the extra information or the redundant information? There are two schemes. These are called coding schemes, yani considering the information and then generating the redundant or extra information. These two schemes are named as block coding and convolution coding. The block coding we are going to study next. The second scheme, convolution coding, it is out of our syllabus, so we will not be studying this. So let's see what is block coding. In block coding, what happens, we divide our message or we divide our data that we want to send to the receiver into blocks. Let's say this is our original data 0 1 0 1 1 1 0 1 0 0 0 and so on. This is the stream of 1 and zeros, and after that we divide our data into blocks. So these are the blocks we divided into blocks of k bits. K is, it could be any number, we can decide it later. So we can make the blocks of few bits, maybe let's say 20, 30, 40. So in that case, k will be 20 or 30 or 40. So first k bits, second k bits, third k bits, fourth k bits, and like that we divide our data into blocks. Each of these blocks are called data words. Data words. And then for this block, block number one, we generate the extra information and append it with the block. Then for the second block, we generate the extra information and append it with the block. Then for the third block and so on, for the last block, we also generate extra information and append it with the block. Now these data words appended with extra information, these are called code words. Remember the first one, when we divided our data into blocks, these were called data words, and the data words appended with extra information, these are called code words. Let's say the length of our data words was k, we generated r extra bits, r redundant bits. So now the length of our code word will be k plus r redundant bits, k original bits. So together the length of the code word will be n. If it is n, it will be equals to k plus r. Another representation of the same, we had our data words of k bits, k bits, k bits, and k bits. We added extra information for each of the data words, which is r of length r. So k bits of data plus r bits of redundant information. Together we say k plus r is equal to n. So our code words are of length n bits. N bits, this k bit will also be n bits, this k bits will also become n bits. To see an example, say our data words are of length 2, 0, 0, 0, 1, 1, 0, 1, 1. We generated one redundant bit with it and we appended it with data word. 0, 0 become triple 0, 0, 1, and redundant information is 1, it will become 0, 1, 1. Similarly, our data of 1, 0, when we generated a redundant bit, it was 1, and now the code word will become 101. Once again, 11 will become 110 because here the redundant information generated is 0. How to generate this redundant information? This topic is coming in the later slides. We will see inshallah in details. Okay, let's see some examples and see. We want to see now how these code words are used on the receiver side to detect, to identify whether there is an error or not. We will go step by step inshallah, see examples in details. First of all, let's assume, please all of you read this with me, that k equals to 2 and n equals to 3. That means k equals to 2 means the length of your data words is 2, and n equals to 3 means the length of your code words is 3, 3, 3, 3, 3. It also means when we look at k equals to 2 and n equals to 3, we also come to know that one redundant bit has been added because original length was 2, final length is 3. So we come to know that one extra bit has been added, has been appended. Table below shows the list of the data words and the code words. Later we will see how to derive the code words from the data word. Assume that the sender encodes the word data word 01. This is the data word that sender wants to send. For example, I am the sender and you are the receiver. I want to send you 01. Okay, I will first of all generate the redundant bit, and redundant bit is 1. I generated the redundant bit. Now the code, this is the code word now that I will send to you. You will receive 011 because you are the receiver. Okay, I sent it to you. You received the number, but what you received is 011. I sent you 011 and you received 011. First of all, you will check whether this is a valid code word or not. You check in from the table 011. Does this exist in the table? Yes, it exists in the table. So you will say yes, this is a valid code word. So what you will say, you know that the first two bits are data bits. This is the data word, and the last bit is a redundant bit. It was used only for error detection. You looked into the table, you found this word into from the table and it matches. It means this is a valid code word. Now it is time to discard the redundant bit. You know the last bit is redundant bit. You will discard this last bit and keep the data, that is 01. This was case number 1. Now we consider another case, which is case number 2. I sent to you 011, but you received 111. Due to network error, instead of receiving 011, you received 111. You are going to check it now, is this a valid code word or not? You check from the table. 111, triple one. Is it here in the table? Triple one? Triple one is not in the table. So you will say that this is not a valid code word. This is a corrupted code word. So now you can do two things. First of all, try to correct it. If you can correct it, okay, fine. If you cannot, then you have to discard it and ask me to send this code word again. Okay, let's go to case number 3. I sent to you 011, but due to network error, you received 000. These two bits were also flipped. Okay, the first bit is already 0. The last two bits were flipped due to network error and you received 000. Okay, so first of all, you will check whether this is the correct code word or not. You will check it from the table. This is the table. Is there 000 in the table? Yes, guys. 000. Is 000 in the table? Salman, check again. Yes, 000 is in the table. Good, mashallah, Khalid, good, Salman. So you will consider that this is a valid code word, and you will discard the last bit because you know that this is the redundant bit, and you will keep the data as 00. The question is, I didn't send you 00. I sent you 01, but due to network error, you got 000, but you considered is correct. However, this is not correct. So it means the detection scheme, this detection scheme, it worked for the first case. It was correct. For the second case, when there was one error, it, because you see here I sent you first bit 0, second and third bit 1 1, but you received 111. It means one of the bits were flipped, first bit was flipped. So if there is an error of one bit, it was detected correctly. However, if there was error when two bits were flipped, check here, I sent you 011, you received 000. So two bits were flipped. This coding scheme could not detect two errors. It could detect one error, fine. But for two errors, it could not detect two errors. So it means each coding scheme, it has its own limitation. It can detect up to some errors correctly. If there are more number of errors, this coding scheme is not working. This coding scheme is not sufficient. So what is required? First of all, we should understand that every coding scheme can detect up to some number of errors correctly, and for the next more number of errors, it cannot detect it. Okay. We will see how we can identify the relationship between number of errors and how many bits we correct. This is coming later, but let's first of all see, can we correct network errors? If yes, what are the errors and how we can correct them? So there is a very less capability for error correction. What is that? Let's see it. Okay, the process for error correction, it is one step more than error detection. First of all, the receiver, it will detect the error. Okay, after detection, if there is an error, it will try to correct it. Here, correction will be here. After detection, there is correction. It is not always possible to correct. In what cases it is possible to correct and how we can correct it, we are going to see. All right. To understand how we can correct error, we are doing it with the help of one example. And this is the example on this slide. Let's all of us read this slide. Let's add more redundant bits to our example 10.0. In 10.2. In 10.2, we had our code bits of length 3. 3 bits code word, 3 bits, 3 bits, 3 bits. But 3 bits, those were for error detection only. Remember, now we want to do something extra. More than our error detection, we want to correct it. So for correction, we need to add more redundant bits. Okay, because only one bit that was used, one redundant bit that could be used for error detection only. For correction, we need to add more redundant bits, more extra information that could be used for error correction, because now we want to do something more. Okay, so we say that we will have our code words of length 5. Okay, assume that the data word 01, this is the data word that I want to send to you. Again, in last example I sent you the same. Now again I'm sending you the same data, 0 1. Okay, this is what I want to send to you. Then I will generate the extra information, that is 0 1 1, and I will append the extra information with my data word, that is 0 1. So this is the code word that will be sent to you. Okay, so I sent you, this should be read as 0 1 0 1 1, but for simplicity I will call it 0 10 11. 0, then after is 10, then after is 11, just for the sake of simplicity. Okay, so I will send you 0 10 11. Okay, this is the code word 0 10 11 that I will send you. But on your side, when you received it, due to network error, you got it 0 1 0 1. I sent you 0 10 11, but you received 0 1 0 1 due to network error. Okay, and see how many bits are changed. First bit is same, second is same, third is same, fourth is changed, fifth is the same. Only one bit, that was the second from the right side, only one bit is changed. Okay, what you will do is, first of all, as like before, you will compare it with your table of code words. You will check it. This is what you 0 1 0 1. You will check it from the table. Does this exist in the table? 0 1 0 1. Is it here? 0 1 0 1. This does not exist in the table. Okay, so you will consider, what will you consider? You will consider that there is an error on the network. Okay, so what you will try to do, you will try to correct it. How do you correct it? You will compare, you know that this coding scheme can detect only one bit error. You have detected it, so you will know that there is only one bit of error, because this coding scheme can detect only one bit of error. So what you will do is, you will compare it with all the code words. All the code words, 1 2 3 4, these are 4 code words. You will compare the number you received with each of the code words. When you compare it with the first code word, how many bits of error are here? First is the same, second is changed, third same, fourth same, fifth is changed. So how many differences are there? 2 bits. Yes, mashallah, Salman. So 2 bits of error. When you compare it with the second code word, how many bits are changed? How many bits are error? Yes, Salman, mashallah. First is same, second is same, third is same, fourth is changed, fifth is same. So 1 bit difference only. When you compare it with the third one, 2 bits are changed. When you compare it with the last one, 2 bits are changed. You know that this coding scheme can detect only 1 bit of error, so you will say only 1 bit of error is here when you compare it with the second. So it means that the correct data word is this one. So you will discard this received code word, you will discard received code word, and you will consider it as this one as the correct code word. So this is the correct code word, and then you will discard the extra information. You know that there are 3 bits extra at the end, so you will discard these 3 bits and you will keep the data word 0 1. This is how you can correct the errors. This is the explanation of what I have told to you. Now we are going towards our next concept. To understand our next concept, we need to revise your previous concepts of XOR. How do you perform XOR? Since all of our computer systems, this is binary, so how do you perform XOR? This is the symbol of XOR, plus with an outer circle. So XOR says when 2 bits are same, 0 0, answer is 0. Same bits, 1 1, answer is 0. When there are different bits, 0 1, answer is 1. Different bits, 1 0, answer is 1. If you have two data words or code words and you perform their XOR, you will perform XOR on bits, individual bits. This is called bitwise XOR. Same numbers 0, different numbers 1, same numbers 0, different numbers 1, and same numbers 0. So this is the answer of your XOR when you perform on these two data words or code words. Yes, Hussein, mashallah. Excellent. Now we are going one step forward and we want to see what is Hamming distance. In Hamming distance, you compare two data words or two code words and you find how many bits are different. For example, see here in this example on the upper hand left hand side, one code word is A, it is 1011001001. Second code word B, and we want to find out how many bits are different here. So this bit is different, third bit is different, seventh bit is different, ninth bit is different. How many bits are different? 3. So we will say that the Hamming distance is 3. So Hamming distance means number of different bits, right guys? How does computer find Hamming distance? We, the human being, we can look at the bits and we can see how many bits are different. We can find the Hamming distance. And the way done by the computer is computer for both of these bit strings, computer will perform XOR. So this is the first bit string A, this is the second bit string, another bit string, these are two bit string. Computer will perform XOR, and you know if the numbers are same in XOR you will get 0. Its numbers are different, you will get ones. So it means, and also zeros for the same numbers. And you see here 3 ones, it means there were differences at 3 places, 1 2 3. So computer will count the number of ones in this bit strings, and this is 3. So computer will say that Hamming distance is 3. It is very easy, you can also do it if you like. So what is the Hamming distance? Hamming distance between two words is the number of differences between the corresponding bits. Okay, let's do some examples and so that we can remember and understand what is Hamming distance. These are two words, 000 and 011. What is the Hamming distance between these two words? How many bits are different here? Two bits are different, so Hamming distance is 2. You can perform XOR on the two words, and this is the answer. In the answer you can calculate number of ones. How many ones are here? 2 ones are here, so Hamming distance is 2. Example number 2. Find the Hamming distance between these two words, 10101 and tetra 10. Okay, how many bits are different here? Yes, 3 bits are different, mashallah. So Hamming distance is 3. You can look at bitwise one by one. First bit same, second bit different, then the next bit same, next bit different, next bit different. So 3 bits are different, Hamming distance is 3. Okay, now we are going to find the minimum Hamming distance. Yeah, how do we do that? This is our coding scheme that we saw before. Now we want to find the minimum Hamming distance of this coding scheme. How do we do that? First of all, we will start with the first code word and compare it with all others. First with second, with third, and then with fourth. The turn of the first is khalas. Then we start with our second code word. Compare it with third, compare it with fourth. Now the turn of second is khalas. come towards the third one, compare it both. Okay, so all these comparisons you find the Hamming distance between all these comparisons. This is first with second, Hamming distance is 2. First with third, Hamming distance is 2. First with fourth, Hamming distance is 2. Similarly, other comparisons, other combinations, and Hamming distance is 2. In all these cases, Hamming distance is 2. So what is the minimum number out of these Hamming distances? These are all same, so minimum number is also the same. Okay, so we will say that the minimum Hamming distance is 2. Let's do another example. In this example, we also find the Hamming distances of all these code words. We can make their combinations like I did before in the last example, and you find the Hamming distance. Their Hamming distances are 3, 3, 4, 4, 3, and 3. What is the minimum number of these guys? Yes, Salman, mashallah, you are right. The minimum of these numbers is 3. So the minimum Hamming distance is 3. Next question is why we are finding the minimum Hamming distance, how we can use it. We can use the minimum Hamming distance for two purposes. First, um, we can use it for to find how many bits of error we can detect and how many bits of error we can correct. This minimum Hamming distance will be used to find the number of error bits that we can correct and the number of error bits that we can detect and correct. Okay, the first step, if we have the minimum Hamming distance, how many bits of errors we can detect. The first objective is detection. Okay, so we can, if our minimum Hamming distance is d minimum, so we can correct one lesser bits, we can detect one lesser bit than minimum Hamming distance. D minimum is equals to s plus 1 as the number of errors. Okay, so our Hamming distance should be, minimum Hamming distance should be one more than the error bits. For example, what does this mean? It means if we want to detect one error, our minimum Hamming distance should be 2. If we want to guarantee the detection of 2 errors, the minimum Hamming distance should be 3. If we want to guarantee the detection of 3 errors, the minimum Hamming distance should be 4. Yani minimum Hamming distance should be one more than the number of errors we want to guarantee detection. I'm saying the same thing once again in the reverse way. If our minimum Hamming distance is 5, how many bits of error we can guarantee detection? 4. If our minimum Hamming distance is 6, we can guarantee the detection of up to 5 bits of errors. Okay, so this is the relationship between minimum Hamming distance and number of bits of errors that can be detected. All right, so see here the same example that we did before. For this coding scheme, these were the Hamming distances that we found, 2, 2, 2, 2. These were all 2. And the minimum Hamming distance here is also 2. Okay, my question is, how many bits of errors we can detect with guarantee? Because our Hamming distance is 2, how many bits of errors we can guarantee detection? Read this line. If our minimum Hamming distance is 2, we can guarantee the detection of 1 error. Second example that we did before, the Hamming distances are 3, 3, 4, 4, 3, and 3. What is the minimum Hamming distance here? Salman, Abdullah, Hussein, Talal, others. What is the minimum Hamming distance of this example? Minimum Hamming distance is 3. How many bits of errors we can detect with guarantee? One lesser than minimum Hamming distance. Our Hamming distance is 3, so we can detect up to 2 errors with guarantee, inshallah. Okay, now we are going towards the correction. Here we studied detection. Okay, what about correction? The relationship for correction is here. D minimum is equals to 2t plus 1. T is the number of error bits that we can correct. Okay, T is the number of error bits that we can correct. The relationship is D minimum is equals to 2t plus 1, or we can write the same thing as in terms of T equals to D minimum minus 1 whole divided by 2. See the previous one, detection. What was the relationship in our detection? It was D min equals to S plus 1. S was the number of bits that we can detect. I have made it gray because we have already studied it. For the correction, the relationship is D min equals to 2t plus 1, or you can write it like this. Let's do one example so that we can remember it. A coding scheme has a Hamming distance D min equals to 4. What is the error detection and correction capability of this scheme? First of all, we will solve it for error detection. The formula for error detection is equals to D min is equals to S plus 1. Okay, what is D min here? D min is 4. So 4 equals to S plus 1. What will be S? S is 3. Or you already remember that if you subtract 1 from minimum Hamming distance, these are the number, this is the number 3, so these are the error bits that you can detect correctly with guarantee. S equals to 3, yani you can detect the error of 3 bits if minimum Hamming distance is 4. So this coding scheme guarantee the detection of up to 3 errors. What about correction? What is the formula for correction? D min is equals to 2t plus 1. So D min is equals to 2t plus 1. T will be the number of error bits that can be corrected. D min is 4. 4 equals to 2t plus 1. You take this 1 on the left hand side. It will be 4 minus 1. So that will be 3. Okay. So 3 divided by 2, that will be 1.5. Can you correct 1.5 errors? No, it means you can correct one error only. So we will round it down. Okay, floor rounding. Normally 1.5 we make it 2. We round 1.5 to 2 because if the number to be rounded is 5 or more, we add 1 to the next number. But here we know these are number of errors, so we have to use our brain, we have to use our logic, and we know that we cannot correct 1.5 errors. It means we can correct only one error. So this coding scheme where D min is 4, it can correct up to 1 errors. Okay, this is the exercise for you. I solved this example for D min equals to 4. You solve this example for D min equals to 5. First question, how many errors you can detect with guarantee when your D is 5? D min, yani minimum Hamming distance is 5. Very simple, okay? First question was very simple. Subtract 1 from here, these are the number of error bits that you can detect correctly with guarantee. What about the next part? How many errors you can correct? Now here is correct. For correction, how do you do that? Very simple, it is half of your number here. Half of your number here, very simple. What was your number here? Detection. Okay, in correction you do the same. First you subtract 1 and then divide it by 2. So it means half of your number that you could detect, half of it you get with guarantee. So you found here number 4, take its half and it will be 2. So you can um, detect up to 2 errors with guarantee. This is the same formula I am talking about. First we subtract 1 from D minimum. If we subtract 1, these are the number of error bits that we can detect. Then take its half. These are the number of bits that we will be able to correct. This is the explanation. Answer of this question is written here. Now we are going towards our next topic for our error detection. Now see guys, we are starting with very simple concepts, and inshallah by the end of this chapter you will learn the technique for the complete techniques, inshallah, at least 2 techniques for the error detection. We are starting with very simple concepts, and then those we will join together and we will see inshallah our overall techniques. Now, the next concept that we are going to learn is linear block codes. You saw today that how we divide our data into blocks, and then there is a very special type of blocks that is called linear block codes. That is called linear block, and the coding scheme. What do we mean by coding? You remember I showed you here today encoder. Yeah, you see here I showed you encoder. So encoder is the software component that generates extra bits and append the extra bits with your data. Then we send it on the network towards the receiver. So this whole process is called encoding or coding. Okay, so this is coding and this is decoding. How do we do coding? We are going to learn now coding. To understand our coding, the first concept we need to understand is what is the linear block coding. Okay, what is the linear block coding, or what is the linear block code? A linear block code says that in a linear block code you take any 2 code words. You can take first or second, you can take second or third, you can take third or fourth, you can take first or fourth, any 2. Take any 2 code words and perform XOR. And if the answer is also in the table, it is called linear block code. Okay, let's take any 2 code words. For example, let's take third and fourth. Perform XOR. When you perform XOR, the first bit is the same, answer will be 0. Different bits, answer is 1. Different bits, answer is 1. So 0 1 1. Is 0 1 1 here in the table? Do you see 0 1 1? See 0 1 1 here. Let's now try some other 2 code words. We try second and third. Perform XOR. Different bits 1, different bits 1, same bits 0. So answer is 1 1 0. Do you see 1 1 0 in the table? Yes, mashallah, mashallah. We see 1 1 0 in the table. So like that, you compare, you take any 2 code words, perform XOR, and if the answer is also in this table, we say this coding scheme is a linear block code. Okay, let's check whether this is a linear block code or not. To check, to confirm is this a linear block code or not, you will make all the combination, first with second, first with the third, and first with the fourth, then second with third, second with fourth, then third with fourth. Like this you will make all the combination and you will perform XOR. If all the answers are also in the table, you will say that this is a linear block code. Okay, so again, very simple. Let's do one example at least and then we will go forward. Let's try it on this time on second and third. Different bits 1, different bits 1, different bits 1, different bits 1, same bits 0. So these are tetra 1 0. Is tetra 1 0 in the table? So we tried it on one. Similarly, you can try it on all others and you will find that all the answers are also in the table. So this is called a linear block code. So summary, in a linear block code, the exclusive or XOR of any two code words creates another valid code word. Yani it is also in the table. Next question. When your coding is linear block code, the minimum number of ones in any code word except the 0 zeros. That is the minimum Hamming distance. See here, we want to find the minimum Hamming distance of this coding scheme. And I inform you that this is a linear block code. In linear block code now you don't need to calculate all the Hamming distances because I told you this is linear block code, so you don't need to find all the combinations. What you need to do is leave the all zeros. This is all zeros, leave it. We are left with now the remaining three code words. Find the minimum number of ones. How many ones are here? 2. How many ones are here? 2. How many ones are here? 2. What is the minimum number of ones? These are all 2's. So the minimum is also 2. So this minimum number of ones is the minimum Hamming distance. Let's say example number 2. Here, find the minimum Hamming distance. And once again, I tell you, this is a linear block code. So in linear block code, once again, you don't need to find all the combination. Look at the minimum number of ones. There are no ones here. Leave this option. This is not included. Here, how many ones are here? 3. Here, 3. Here, 4. Okay. So what is the minimum number? 3, 3, 4. Minimum number is 3. So the minimum Hamming distance for this coding scheme is 3. Now we are going towards, Alhamdulillah, this is time that we learn one coding scheme, one error detection scheme that is called cyclic code. And if you remember your Ethernet frame, this is the picture of your Ethernet frame. And you remember your last field in your Ethernet frame, it was CRC. What does this CRC stand for? It stands for cyclic redundancy code. Cyclic redundancy code. So we need to understand first of all, redundancy means extra information, because this information is extra that is appended with our data. Why do we append it with our data? We use this information for error detection. Okay, how do we generate this information? Cyclic code, we need to understand how cyclic code works. Redundancy means extra. Okay, so actually it is cyclic code. How do we generate our cyclic code? How do we use the cyclic code? We are going to see next. First of all, what is cyclic code? This is we are going to see with the help of this example. This is a cyclic code with cycle of 7 code word bits, 4 data words. See here our data words, length of data word is 4. Yani 4 bits in our data words and 7 bits in our code words. See, these are our code words. Code words 7 bits, 7 bits, 7 bits, 7 bits. So we come to know our original data word was 4 bits and our code word is 7 bits, so we are generating 3 extra bits here. This is what we come to know from here. Okay, we are going to study now what is a cyclic code. The property of cyclic code is take any code word, any, these are the code words and these are also code words. Take any code word. Let's say we take this code word. Okay, you can take any, and then you rotate it left or you rotate it right. The answer will also be the next number will also be in the table. If it is in the table, it is called a cyclic code, because then you will complete the cycle. Let's see how. I want to take this number for example, and I want to shift it left. When we shift it left, we push it from the right side. Push it from the right side, this 0 will come out and this will come back to the right. This is called left rotation. Rotate it left. To rotate it left, yani towards this one, push it from. When you push it from the right, this 0 will come out here and this will go back to the first position. What is the new number? The new number will be 100. When you shift it left, this 0 will come here. So the new number will be 100,110. 100,110. Once again, I repeat, guys, I am shifting it towards left. Shift it towards left. This number from the left, it will come out and it will go back to the right side. So what will be the new number? 100,111 and 0. It's here. 00,111. Yes, it's here. Now again, shift it left or shift it right. You can shift it any number of times. Shift it once, shift it twice, shift it thrice. No matter how many times you shift it left or right, the new number is again in the same table. That means it is cycle. These numbers are rotated in the cycle. Okay, cycle, cycle, right shift or left shift. That is why these are called cyclic code, because when you shift it in the cycle, either left or right, the new number is again in the same table. That is why these are called cyclic codes. Once again, a revision. When we divide 27 with 5, 27 is called dividend or dividend. This is the divisor, and we are looking for, what we are interested is the last number which is remaining, that is called remainder. We are not interested in our quotient, we are interested in our remainder. Let's use it. Okay, our next topic is how to generate extra bits for our cyclic codes and use it for our error detection. You see here these pink numbers, how to generate these pink numbers, how to make the cyclic codes, and how we can use these extra bits for our error detection. This is the next topic coming. I will explain this to you with the help of a picture and with the help of an example. The process is written here, all in the text. It's easy if we consider it with the help of this picture. Okay guys, be attentive now. This is the sender side. On the left side, sender. On the right side, this is the receiver side. Sender, let's say I am the sender and I want to send you a data word. It consists of 4 bits. Bit 0, bit 1, bit 2, bit 3. A0, A1, A2, A3. This is my data word that I want to send to you. Its length is 4 bits. And me, sender, you, the receiver, we both agreed that we will generate 3 extra bits. Okay, so what I will do is I will add 3 zeros at the end of this data word. At the end of this data word, I will add 3 zeros. And then I will give this new number to a generator, to a software. Its name is generator or encoder, like I showed you at the start of this chapter. And the generator will divide this number which I input to it with the divisor. You, me, sender, and you, receiver, we both agreed that we will use this divisor. Divisor will be a 4-bit number. The generator, it divides this number that I gave it as an input with this divisor, and it will find the remainder. This remainder. The generator will find the remainder. After the division, it will find the remainder and put the remainder here. Remainder will be 3 bits because I added 3 bits, and divisor was 4 bits. Remainder is always 1 less than the divisor. Divisor are 4 bits, remainder will be 3 bits. If divisor is 3 bits, remainder will be 2 bits. If divisor is 2 bits, remainder will be 1 bit. Okay, so fine, my data word A0, A1, A2, A3, and the remainder bits, remainder 0, remainder 1, remainder 2, R0, R1, R2. Now these 7 bits, I will send it to you. What you will do is, you will perform the same thing. You will divide this number, this whole number, with the divisor. Okay, if your remainder is 0, all zeros, this is your remainder. It is also called syndrome. Remainder or syndrome is the same thing. If your remainder is now 0, 0, 0, you will accept the data word, otherwise you will discard the data word. Okay, so let's do it with the help of one example, and then we finish our today's lecture. So this is my data that I want to send to you, 1001. This is my data, and you and me both together, we agreed that we will use this number as divisor, 1011. Okay, so I will keep my number and I will add 3 zeros because we agreed that we will add 3 redundant bits. Okay, so we want to add 3 redundant bits, so I will add 3 zeros. This is my original data, 1001, 1001, 3 extra zeros. This number now I will divide it with the divisor that you and me both agreed upon. How to divide? Now this is a little interesting. Please pay attention. How to divide it? This is 1011. If your first bit here is 1, you multiply your answer, your quotient will be 1. If your first bit is 0 here, your quotient will be 0. Okay, here your first bit is 1, your quotient is 1. Multiply quotient with the divisor. When you multiply this divisor with 1, same number comes here, 1011. Okay, next you perform XOR on these two numbers. You do not subtract. In our normal division we subtract, but in our binary division we perform XOR. Same numbers 0, different numbers 1, same numbers 0. First bit is always cancelled, so we don't do anything with the first bit. It is time to bring the first 0 down here. We have 4 bits again. Look at the first bit. It's 0, your quotient is 0. Multiply this 0 with your divisor. Anything multiplied by 0 makes it 0. So these are all zeros. Again apply XOR on these two bits, on these two words. Same number 0, same number 0, different numbers 1. Leave the first bit, it is always cancelled. Bring the second 0 down here. Your word is 1000 now. We need to divide it with divisor. What is the first bit? 1. If your first bit is 1, your quotient is 1. Multiply this 1 with the divisor. Anything multiplied by 1, same number comes. Perform XOR on these two words. Different numbers, 1. Different numbers, 1. Same numbers, 0. First bit is cancelled. We don't do anything with the first bit. And now we bring the last 0 down. Again, we need to divide this number with the divisor. Look at the first bit. What is first bit? 0. If first bit is 0, your quotient is 0. Multiply this quotient 0 with your divisor. Anything multiplied by 0 makes it all zeros. Perform XOR. Same number 0, different numbers 1, different numbers 1. No more zeros here, no more numbers here. This is your remainder, 110. I will append this remainder with my data word. What was my data word? 1001. This was my data word. I will append the remainder 110 with my data word, and I will send this number to you. This is my code word now. Okay, this is my code word, and I will send this number. Now this is how we generate extra information for cyclic code. I generated this extra information, which is actually my remainder, and I will send it to you. You are the receiver. Okay, so we can make a question here. What will be the 7-bit code word in cyclic redundancy code if the data word is 1001? See, if my data word is 1001 and the divisor is 1011 and the divisor is 1011, show the details of your calculation. This is the question that I can ask you in exam, and you will show me all these calculations. And you will show me all these calculations in the exam. Okay, what happens on your side? Two possibilities. First possibility is success, that you receive the same number that I sent to you. You will receive the same number, 10011110. There is also possibility that you receive one error. Okay, so we will see both of the cases. In both of the cases, you will do the same division, but now you will divide the number. This is the number to be divided. Okay, this is the number you want to divide it with the same divisor. You divided it, you will check the remainder. Process of the division is the same as I explained you in the last slide, but here what you are interested in, it is the remainder. It is also called syndrome. If the remainder is 000, it means success. It means there is no error. So in that case, you will discard the redundant information that is in pink. You will discard it because this was appended only for error detection. Actual data is this one, 4 bits. So you will accept the data word. In case if there is any error, like we see here, 1 bit has been changed due to network error. It was originally 1 and now it has become 0. Okay, so what will you do? Again, you will do the operation is the same, but in case of error, your remainder is not 000. It is anything other than 000. You see here remainder different than 000. It means there has been some error in the network transmission. What will you do? You will discard this code word. You will discard this code word and you will ask me, doctor, there was some error because my syndrome or my remainder is not 000. Can you please send the data again? So I will send you this code word again. Again, you will perform, you will check it. If your remainder is 000, you will accept it, otherwise you will discard it.